Hi everybody. Today in this video I want to discuss with you the forced convection heat transfer over another geometries. In the previous videos we discussed the conduction heat transfer at the first video, and after this we spoke about the forced convection over a flat plate. And now I will discuss the forced convection over another types of geometries. But before we go through, we just want to remember the main equations to use in case of the horizontal flat plate. So if I have a flat plate here with a length of L, and I want to calculate the local heat transfer coefficient at any x or at any point away from the leading edge of this plate, I can have the Nusselt number or the local Nusselt number by using these equations. So in case of laminar, which is defined as a Reynolds number less than 500,000, the Nusselt number or the local Nusselt number, it will be given by this equation, and in case of turbulent it will be given with this equation. Please remember that the Reynolds number is calculating with respect of the length of this horizontal plate. Great. By understanding what is the forced convection heat transfer coefficient over a horizontal flat plate, we can have this value of heat transfer coefficient, and we can calculate the heat transfer rate. Okay. Now we can go through the new topics or the new subject which I want to discuss with you today. It will be consisting of three points or three main titles. The first one, it will be the forced convection over another geometry or other geometries, and the second point, it will be the forced convection inside a tube or a pipe. And the last point which I want to discuss with you, what is the difference between the natural or free convection and the forced convection. So let's start with the first one, forced convection over other geometries. Generally we will have two types of other geometries, which is the most popular geometries in real life, if it is single tube or duct, or if it is a bank of ducts or tubes together. Let's start with a single tube. So if I have a tube like this, and I have a flow moving over the external surface of this tube, okay, I can have the flow stream lines in this shape. In real life or in the actual flow, it will be taken this shape, and you can see here there is a turbulence flow here in this area by having a three-dimensional vertices. So this is a turbulent flow, so it will be a mix of laminar and turbulent flow. But if we consider it like it's an ideal flow, we will have very smooth streamlines, and this is not exist in real life. Okay, so how to calculate the average heat transfer coefficient for this geometry or for a single tube. Okay, the average heat transfer coefficient can be calculated by knowing the average Nusselt number with respect of the tube diameter, and the Nusselt number is given by this equation, which is consisting of the Reynolds number and the Prandtl number, but I have here two different parameters which I need to know the value of it, which is C and M. C and M can be given by these values with respect of calculating the Reynolds number. Remember that the Reynolds number in this case and the Nusselt number as well, it will be given with respect of the diameter of the tube as we see here in this equation. So by knowing all of these parameters, I can have here is a heat transfer coefficient or the average heat transfer coefficient, and from this one I can calculate the heat transfer rate. Great. So this is the first geometry I want to discuss with you today. What if I don't have a single pipe, but I have a bank of pipe or a group of pipes? I need to calculate the average heat transfer coefficient for this geometry. But remember, we will not consider it like just a single individual pipes, but we will deal with this issue as one geometry, like a band or a group of pipe or a bank of pipe. So I consider it like just one geometry. We can have the average Nusselt number given by this equation. But this equation, we have here a new parameter or a new term which is need to be calculated, which is known as the Prandtl number with respect of the surface or the tube surface. Okay, so what is the difference between Prandtl number, which is normal one, and the Prandtl number with respect of S? The Prandtl number or the normal Prandtl number, it will be calculated at a temperature is called the mean temperature or the fluid mean temperature, but Prandtl number with respect of S, it will be calculated as the surface temperature or the surface area temperature. For example, if I have here this is the bank of the tubes or pipes, and I have here that the flow at the inlet has a temperature Tn, and I have the flow after touching these surfaces coming out with a temperature is called T out. So the mean temperature, it will be T in plus T out divided by 2, the average temperature of the fluid. But here I have the surface temperature, which is the temperature of the external surface area of these tubes, assuming that all of the tube have the same surface temperatures. Okay, in case of a different surface temperature of each tube in this group, it will be another story. We will not discuss it in this video. Okay, so I have here U, which is the velocity of the free stream or the free stream of the fluid, and I have the temperatures in and out. I can calculate the Nusselt number easily from this equation by having Prandtl number, and I have Reynolds number with respect to of diameter, and I have here M and C, which is given by values from the above here, if it's based on the types of the flow itself, like laminar or turbulent. Great, so by knowing the heat transfer coefficient, I can calculate the heat transfer rate between the tubes and the flow. Remember that in case of the fluid moving in, or the temperature at the inlet, which is Tn, is less than T out, which is means the fluid getting hotter. That means that the tubes or the pipes as the initial condition is it having a temperature higher than the flow or the fluid. But in case if the Tn more than T out, which is meaning like the fluid getting cooler because the flow was initially hot, and after touching the tubes or pipe surfaces getting cold, which is mean is the heat transfer moved from the fluid to the tubes or the bank of tubes, or the tube surface was cold initially. Okay, so this is like you have to understand how to feel the heat transfer process, so it will be easier for you to deal with it. Okay, so now we understood in case how to calculate the heat transfer coefficient in case of single tube or in case of bank of tubes. Okay, the second point which I want to discuss with you today is what if I have a flow inside a tube, not at the outside surface area, but touching the inner surface area of the tube. Okay, initially the flow get moving at the beginning of this tube with a velocity is called u, let's say, and because of the inertia of the flow, there is a boundary layer will be generated, and this boundary layer it will be merged at a point here, and after this point the flow will be fully developed, which is a fully turbulent flow. Okay, so let's say for example that the flow is starting with a laminar, and then it will go to the transition mode as we discussed in the previous video, and then it will be fully developed flow after the merging point of these two boundary layers. Okay, how to calculate the average heat transfer coefficient? This is our objectives. Okay, the heat transfer coefficient or the average heat transfer coefficient can be given by this equation, like by Reynolds number as well. Like here the heat transfer coefficient is given by this equation in case of turbulent, and in case of laminar it will be given by this equation. I know that the Reynolds number it will be 4 or equal to 4, so I can calculate the heat transfer coefficient. But remember that Reynolds number in this case, even the Reynolds number, it will be calculated with respect of the hydraulic diameter. So now I want to understand how to calculate the hydraulic diameter. Hydraulic diameter is a function of the cross-section area of the geometry and the weighted perimeter, which is mean like if I have for example a rectangular cross-section area duct, I can calculate the hydraulic diameter from this equation, and if I have a circular cross-section area duct, the hydraulic diameter it will be equal to the diameter of this pipe. Okay, what if I have an open channel cross-section area, or if I have half full pipe as it's shown in this shape or in this figure, sorry. So the hydraulic diameter it will be calculated from these equations as well. Generally, the hydraulic diameter is equal to 4 times the cross-section area of the geometry divided by the weighted perimeter. Okay, and weighted perimeter is the sum of all of this touching fluid lengths, or it's the sum of all of this wetting lengths or wetting sides of this cross-section area. Okay, so in case of laminar or turbulent flow, we have the Reynolds number and we have the equations which we can find out what is the heat transfer coefficient by calculating it. Remember that we have here two different value of n, which based on the relation of the flow and the surface area of the pipe. So if I have a cold fluid, for cooling fluid it will be 0.3, and if I have a fluid for heating it will be 0.4. Okay. Okay, great. Now by this we have finished the forced convection heat transfer over three types of geometry, or with a relation of three types of geometry, which is the horizontal flat plate, which is a single pipe or a bank of tubes, and we have as well the internal flow inside a tube with a diameter h. Okay, what is the difference between the forced convection and natural convection heat transfer? Natural convection, there is no external force which is moving the flow or which is driving the flow, but this is the forced convection, we have an external force, but in case of natural convection we don't have, there is no external force, but the flow it will be moved, or the heat transfer mechanism it will be dominating by the buoyancy force. What is the buoyancy force? Imagine if I have a horizontal flat plate like it's shown here, and we have here the fluid layers. Okay, imagine the nearest nearest layer of the fluid near to the flat surface, it will getting hot, and the density of this layer it will be less, and the buoyancy force it will move this layer to the upper surface or to the free surface of this fluid, and the colder or the colder layer it will be go down like this to replace the empty volume. Okay, so we have a free circulation movement by the changing of the density of the fluid, and this movement is driven by a buoyancy force. Okay, so we can understand from this symbol explaining that the Nusselt number in case of natural convection it will be a function of the buoyancy force, because the buoyancy force is the force dominating this movement or is a flow movement instead of an external force such as fan or a compressor. Here this table showing for you like what is the difference or how big difference between natural and forced convection in case of liquid or gas fluids. In case of liquids, the heat transfer coefficient in natural convection it will be between 50 to 1000, but in forced convection it will be 1000 to 20,000, and in case of gases it will be in case of natural it will be between 2 to 25, but in case of forced convection will be between 25 to 250. That's why in real applications, in case of chillers or air conditioning or any cooling system, we will have a forced convection heat transfer, not natural, because the heat transfer coefficient in case of forced convection will be much higher than the natural one. Okay, so we discussed before what is the physical meaning of the Reynolds number, which is the ratio between the inertia and viscous force. But now I want to introduce for you a new dimensionless group, which is called a Grashof number. And the Grashof number physical meaning means the ratio between the buoyancy force and the viscous force. So here there is a buoyancy force which is dominating the natural convection movement. Great. Here there is a term in the Grashof number calculation which is known as the coefficient of expansion or the volumetric coefficient of expansion. By knowing, and this is given value, it will be given when you're calculating your equation or when you're designing a new system. Okay, so I can calculate easily Reynolds number and Grashof number, and by understanding both of them I can calculate the average Nusselt number with respect of L, which is the length of the geometry, and this is given by this equation in case of vertical surface, in case of laminar and turbulent flow. Remember that the Grashof number is a new parameter to be calculated for natural convection because it is including the buoyancy force. And as I mentioned before in the forced convection, that every single property of the flow properties it is calculating at the mean film temperature, which is the inlet temperature plus the outlet divided by 2. Okay, so now we understood the natural convection for one geometry only, which is the vertical surface. Just to give you an idea how the natural convection are to deal with the natural convection is completely different than the forced convection. But in real life there is no a device or no air conditioning unit, for example, is designing based on natural convection. This is very real. Okay, so I hope this video gave you an idea about how to deal with the forced and natural convection, and at the next video or in the next video I will discuss with you is radiation heat transfer, and then we can go through another interesting topic which is important for heat transfer engineers. Thank you very much and see you again. Thank you.